Black holes and revelations, gravitational wave background. Muse, a well-known rock band, was obviously onto something with their 2006 album Black Holes and Revelations. I really recommend giving it a listen. But first, let's discover what the universe has been keeping from us. We keep hunting for ways to build time machines, only to discover that they have always existed. As time passes and technology advances, we discover new ways to glimpse through time, giving us a great chance. One such intriguing concept is gravitational waves, which are ripples in the fabric of space-time created by the movement of enormous objects. Albert Einstein anticipated these waves in his general relativity theory more than a century ago, but they remained elusive until lately. In a groundbreaking finding, scientists found weak echoes of the gravitational wave background, ushering in a new era of astronomy and revealing a previously unknown element of the universe. If this backdrop exists, it calls into question our understanding of the universe's hierarchical creation, as mergers of enormous objects would have occurred so early on, implying that they existed at all. Without them, we would have been completely ignorant. We'll explore how quasars helped us discover the cosmic microwave background and how pulsars revealed something we never expected to see. What are quasars? Quasars, which stands for quasi-stellar radio source, are extremely bright and distant objects seen in the remote reaches of the universe. They were first discovered in the 1960s, but their true nature remained unknown for many years. Astronomers initially thought they were stars because to their point-like appearance, but as technology evolved, these brilliant objects revealed their actual identity. These lighthouses are found in the cores of active galaxies, surrounded by swirling disks of extremely hot gases and dust. Every quasar has a black hole, which is a tremendous gravitational force that devours anything that gets too close. As matter falls into the black hole, it produces an accretion disk, which is a churning, chaotic cyclone that emits massive amounts of energy in the form of radiation. This radiation is what gives quasars their incredible brightness. In fact, they are among the most luminous things in the cosmos, outshining even the Milky Way, which has over 400 billion stars. This is merely the energy emitted by one of the quasars. But what genuinely distinguishes them is their extreme isolation from us. They exist in the furthest depths of space and time, billions of light years from Earth. The light we see from quasars today originated billions of years ago, providing a look into the primordial universe. It's like gazing into a time machine and seeing the universe as it once was. And that as astronomers continue to examine quasars, they discover a wide range of exciting behaviors. Some quasars display redshift, a phenomena caused by the universe's expansion, which stretches light waves and shifts them to the red end of the spectrum. This redshift reveals important information about the universe's expansion pace and cosmic history. What are pulsars? It is easy to confuse quasars and pulsars, although they are two distinct sorts of objects in the universe. Pulsars are one of the most exciting astronomical phenomena, and believe me, the universe is full of wonders. They are the remains of huge stars that went supernova. During these gigantic explosions, the star's core collapses under its own gravity, resulting in the formation of a neutron star. Consider this: a neutron star the size of a city, packing more mass than our sun into a little space. These dense objects are the cosmic equivalent of a black hole's overachieving younger sister. But here's where it gets really interesting. Pulsars contain magnetic fields that are far more powerful than any magnet you've ever seen. Now let's look at why these cosmic lighthouses are named pulsars. As the neutron star spins on its axis, its tremendous magnetic field emits beams of electromagnetic radiation from its magnetic poles. These beams sweep over the galaxy with remarkable precision, similar to a lighthouse beam cutting through the darkness. The most amazing thing is that as the radiation beams sweep towards us, they seem as regular pulses of energy. It's like the universe's own Morse code, sending signals from the depths of space. These pulses can be as consistent as your favorite morning routine or as unpredictable as your cat chasing a laser pointer. Regardless, they never fail to capture our imagination. We are talking about hundreds of rotations per second. Others take their time, slowly completing a spin over a few seconds or minutes. Quasars and cosmic microwave background. However, quasars have another exciting property that has recently piqued the interest of astronomers. They can measure the universe's new backdrop. The universe's background corresponds to the cosmic microwave background, a glow of radiation left behind from the Big Bang. This radiation is uniform and fills all of space, allowing a glimpse into the early universe when it was only 380,000 years old. This is where the quasars come in. Quasars can operate as backlights by shining their light across the intergalactic medium, which is the immense expanse of gas and dust that fills the space between galaxies. As this light travels across the cosmic medium, it interacts with the gas, leaving minor fingerprints in its spectrum. These imprints, known as absorption lines, disclose crucial information about the gas's properties, including temperature and density. Astronomers can trace the distribution and history of gas in the cosmos by investigating the absorption lines in quasar spectra, which provides insights into galaxies' formation and interactions with their surroundings. However, quasars are especially effective for assessing the universe's new background because of their ability to probe a specific epoch in cosmic history. Quasars exist during the cosmic dawn, when the first galaxies formed as the universe transitioned from a neutral to an ionized state. During this cosmic dawn, the universe was undergoing a major shift, with radiation from quasars interacting with neutral hydrogen gas, forcing it to become ionized. By investigating quasar absorption lines, scientists can precisely determine when and how this ionization process occurred, as well as trace galaxies' expansion in the building of intergalactic gas across cosmic time. Quasars function as time machines, allowing astronomers to view back into the universe's early history. Scientists may determine how much hydrogen gas was there at different times and how it changed over time by researching the many types of gases found in quasars. This helps us comprehend how galaxies are generated. Pulsars and gravitational wave background. As amazing as quasars are, and how much they have helped us understand our origins, smaller pulsars are equally useful. Astronomers achieved a major scientific discovery as a result of their contributions. We finally heard the cosmic symphony of gravity waves echoing across the universe. After years of investigation, scientists have discovered the gravitational wave background, or low-pitch hum of these waves. This background is thought to be the remnant echoes of events that occurred shortly after the Big Bang, including the merging of supermassive black holes around the cosmos. This will reveal a wealth of knowledge about how our universe evolved and whether supermassive black hole encounters acted as accelerators for structure building. In a highly anticipated and concerted effort, scientists from all across the world unveiled their discovery. The signals were discovered to be consistent with the presence of the most massive black holes in the entire universe, giants weighing billions of suns. While the particular cause of the hum is unknown, this discovery provides strong evidence for the presence of gravitational waves. Let's look at how pulsars disclosed this to us. It was far from trivial. The scientific community agreed to begin observing millisecond pulsars for a period of 15 years. Millisecond pulsars rotate at incredibly high rates with a frequency of milliseconds, making them the ideal natural clock for precise work. Because of the precision with which we observe pulsars, we can identify even the smallest changes in the time it takes for their light to reach us. This is known as pulsar timing. Before I continue, I'd like to provide you with some useful information to help you get through the video. Gravitational waves stretch and squeeze space-time, causing the pathway of light, also known as geodesic, to bend as they pass through it. Because the path of light has been bent, it will take longer to reach its destination. That is exactly what astronomers have witnessed from pulsars. The time it would have taken their light to reach us if gravitational waves had not created any deviation was shorter than observed. And over the entire period of observation, which led them infer that those gravitational waves are, in fact, a constant background rather than a single recorded collision between enormous objects, as they are supposed to detect. This graph shows how the conclusions of a gravitational wave background are validated by evaluating the fluctuations in the arrival timings of 67 pulsars, yielding a total of 2,211 distinct pairs. The dashed line represents the predicted correlation patterns between these pairs, which are influenced by passing gravitational waves. On the other hand, the solid line depicts the predicted correlations in the absence of the backdrop. The nanograv's observations represented by blue data points show the expected increase in correlation for both small and large separations, indicating the presence of a gravitational wave background signal. The frequency of this background is extremely low, leading to the notion that the collisions were created by the merging of minuscule black holes or neutron stars with masses less than a few hundred solar masses. Possible theories. Astronomers have discovered probable black hole couples using various telescopes, but they now have a new tool, gravitational waves. These waves can guide them in the right path while searching for electromagnetic waves and studying black hole couples in depth. Chungpei Ma, a renowned astronomy and cosmology professor, is leading a research to investigate the 100 closest supermassive black holes to Earth. Her primary purpose is to identify signals of activity that indicate a binary pair. Nanogravs will then direct its pulsar timing array to that region of the sky to search for gravitational waves. Black hole binaries generate these waves for millions of years before merging. Other proposed explanations for background gravitational waves include dark matter axions, primordial black holes, and cosmic strings. However, the researchers feel that black hole pairings are the most likely explanation. To show this, they must determine how much the gravitational wave signals change over the sky. Binaries should provide substantially larger variability than other sources. This is where the actual work and excitement starts. The team is working hard to enhance its observations and obtain a better understanding of the populations of early supermassive black hole binaries. This leads us to the finish of our voyage. From quasars to pulsars, we've looked at how these incredible phenomena have helped us solve the universe's secrets. It's like a never-ending game of cosmic hide-and-seek, with each finding raising new questions. But that's what keeps us scientists on our toes and pushing the boundaries of knowledge. So until the next mind-blowing discovery, keep looking up to the sky and dream big. Who knows what additional cosmic wonders are waiting to be discovered? Keep being curious, nerdy, and exploring the infinite cosmic playground that is our universe. See you next time. Thank you for viewing, and we'll see you in the next video, when we'll look at more exciting events in our universe. Don't forget to like and subscribe to our channel to keep up with our latest videos and most intriguing topics.